What's the connection between a robot which pours drinks, a 19th century winding engine, a child's folding pushchair, and a telescopic umbrella? Well, they're all systems which involve movement. In fact, they are examples of kinematic systems. Let's take a closer look at the umbrella. As I open and close it, the component parts move with respect to one another. And it's the same story with this folding pushchair. As I fold it down, you can see that the struts here and here move with respect to one another. And it's a similar situation with the robot and winding engine. In fact, there are many, many thousands of examples of such systems in everyday life, systems which involve movement. But some of these systems are actually designed so that they do not move. In fact, if you look around, you will see that in many cases, movement is a positive disadvantage. These types of system are structures. They are special types of kinematic system. However, in this program, we are going to concentrate on systems which do move, and in particular, those systems which are concerned with mechanical manipulation. In manufacturing industry, there are very many examples of such systems, some of which are designed to move objects from A to B, to bring two or more objects together, to weld in a particular spot, or to spray paint in a particular direction. These are all solutions to the problem of mechanical manipulation. And that problem is this. Given an object in three-dimensional space, be it a pen, a welding gun, a paint spray nozzle, or a gripper on a robot manipulator, how can we move it in a controlled way so that we can position it at any point within a certain volume and orientate it in any direction? This program will seek to answer that question, and we do so by looking at kinematic systems in general.
Just to show that there's more to its repertoire than pouring drinks, let me introduce you to PUMA. That's an acronym for Programmable Universal Manipulator for Assembly. And it's one of a range of robots that's manufactured by Unimation Limited at their factory at Telford in Shropshire, which is where we are now. The PUMA is designed to solve precisely the sort of manipulation problem we're interested in, that of moving objects from one place to another and one orientation to another in three-dimensional space. And to understand how PUMA solves that problem, we're going to have to look in some detail at kinematic structure. Now, you remember from the text that this is going to involve identifying two fundamental types of component, links and joints. The links are the rigid parts of a system, like these, and the joints are where links come together. We're going to make things simple by assuming that the systems we're looking at have only binary joints. That is, joints where we've got just two links coming together. And we're also going to assume that all the links are rigid. We haven't got any flexible members. Well, now, let's concentrate on the joints first of all. Now, in the case of surface contact, we're going to have one of those 6 lower pairs defined by Rouleau. Of course, when Rouleau did his analysis in the 19th century, the prime moving power of technology was steam.
Here we have some examples of lower pairs in this old winding engine, which dates from about 1850. Over there are a couple of revolute pairs. And down here, there's another revolute and a prismatic pair. And Richard has some models over in the workshops.
All fixed?
Yes, okay, Richard, all yours.
Thank you. It's easier to see what's happening on these models. And the first one is of the prismatic pair that you saw out on the engine. And you can see from the model this allows a sliding motion, a translation, but I can't turn it at all. So there's only one way in which I can move one link relative to the other. And that means that if I want to specify the position of one link relative to the other, I only need one parameter, the amount it's moved. And so we say that this joint has 1 degree of freedom. Now the next joint is the revolute pair, and again you saw this out on the engine. Now here I can have a turning motion, but I can't have any sliding at all. And so again, there's only one way I can move one link relative to the other. Only one parameter, the amount that the link has turned, is needed to specify the position of one link relative to the other. And again, therefore, the joint has 1 degree of freedom. The third one is the screw pair. Now that allows me both a turning motion and a translational motion. But the two are linked together. They're linked by the pitch of the screw threads, that is the angle at which these threads are cut. And therefore, really, there's only one motion possible there as well. And I need only one parameter to specify the position of one link relative to the other. This can be either the amount I've turned it or the amount of translation. And in fact, the screw pair is an interesting one because the other two can both be thought of as a special case of a screw pair. The revolute pair, I can turn it as much as I want, but I get no translation. And so it's like a screw pair, but with 0 pitch, with vertical threads. And on the prismatic pair, I can get as much translation as I want without any turning at all. And so it's like a screw pair, but with horizontal threads, that is, with infinite pitch. We've got an example of another kind of joint on this drilling machine that dates from about the turn of the century. The joint is a cylindric pair, and the links are the body of the drill here and the shaft, which both rotates and has an independent translational motion. And on our model of the cylindric pair, you can see that this joint, in fact, acts like a combination of the prismatic pair that allowed sliding and the revolute pair that allowed turning. So now I've got two motions on this joint. I've got to give two parameters to specify the position of one link relative to the other, the amount of sliding and the amount of turning. And so the cylindric pair has 2 degrees of freedom. Now, here's a familiar-looking joint. You probably know it as a ball and socket, the sort of thing you have on a car mirror. But in Rouleau's terminology, it's known as a spherical pair. And this joint allows 3 different rotations. One about a vertical axis, like this. One about a horizontal axis this way, that's like that. And the other about the other horizontal axis, like this. So we've got to specify 3 parameters to give the position of one link relative to the other, 1 parameter for each of those 3 rotations. And the spherical pair, therefore, has 3 degrees of freedom. And finally, we've got the planar pair. This joint isn't used all that much because of the difficulty of controlling it. One link has complete freedom to slide anywhere over the other. And you can think of this as a combination of 2 prismatic pairs, one sliding that way and one sliding that way, and 1 revolute pair turning about a vertical axis. Again, there's 3 different motions, and therefore we've got 3 parameters needed to specify the position of one link relative to the other, 3 degrees of freedom. Well, that's all 6 of Rouleau's pairs, but what's all this got to do with the analysis of kinematic structures? What, for instance, has it got to do with Puma?
The Puma is designed completely around revolute pairs. There are 6 of them arranged in series. So we have the first, second, third, fourth, fifth, and sixth. Let's take a closer look at how the axes of these pairs are arranged geometrically. The first revolute axis and the second intersect at 90 degrees inside this link. The second and third are parallel. The fourth, fifth and sixth axis all intersect in a single point at the wrist, the fourth and fifth being at right angles to one another, and so also the fifth and sixth. How does this system solve the manipulation problem? Well, the last link in the chain, the gripper, has to hold and position an object in space. How many parameters are required to do this? If we take a look at the gripper, to position an object, it has to move in the X direction, the Y direction, and the Z direction independently to reach any point within its workspace. Furthermore, to orientate an object, it has to be able to pitch, roll, and yaw, which makes a further 3 parameters. So there are 6 degrees of freedom required at the gripper in all, 3 for translation and 3 for orientation. The Puma system achieves this 6 degrees of freedom by having 6 revolute pairs in series, each revolute pair contributing 1 degree of freedom. But of course, other arrangements are possible.
This is another of Unimation's robots, and you can see it's built on a much bigger and heavier scale than Puma is. And there are some other differences as well. First of all, it uses not only revolute joints like this one, but also prismatic joints like the hydraulic ram inside this concertina dust cover. It uses prismatic joints because they're better at handling the heavy loads that this robot is designed to cope with. And then further up, we've got another difference. We've got a vertical link here with a prismatic joint. That's connected by a horizontal link inside here. There's the main vertical link and the horizontal link across the top, making a complete loop of links and joints that we didn't have on Puma. So we've not only got different types of joints, we've also got them connected together in a different kind of way. And that raises an interesting general question. If I know what type of links and joints I want, how can I connect them together and still be sure that I've got the right number of degrees of freedom back here at the end?
To answer Richard's question, we need to look in more detail at the kinematic structure and the geometry. 2 systems have the same kinematic structure if they have the same interchange graph. Remember that on an interchange graph, the joints are represented by edges and the links are represented by vertices. Here we have a model of a system with the same kinematic structure as the Puma. It therefore has the same interchange graph. There are 7 links, which are these dumbbell shapes, interconnected by 6 revolute pairs. Its interchange graph therefore has 7 vertices connected in a simple chain by 6 edges, marked with R to represent the fact that they're revolute pairs. This end link, or gripper, as it would be in a manipulator, has 6 degrees of freedom. It can move in X, Y, or Z direction, making 3 freedoms of translation, together with yaw, pitch, and roll angles of orientation, making 6 in all. We can change its kinematic structure quite easily. if we remove this fixed link like so, create a new joint, connect it to the gripper here. So here we have the original fixed link. The kinematic structure has now changed, and the interchange graph has changed from a simple chain of 7 vertices to a closed chain of 7 vertices. How many degrees of freedom has this new system got? We've introduced an extra joint. You might expect it to have 7 degrees of freedom now. But in fact, if I hold this link fixed and move an adjacent link here, the whole system its motion is determined by a single angular variable. So it has only 1 degree of freedom. The extra joint has not introduced an extra freedom, but removed 5. Okay, so we've now looked at the kinematic structure. What about the geometry? Here we have a link from this system. It is a binary link because there are 2 revolute pairs on it. Here's one, and its axis is marked with this white rod. Here's the second one, and its axis is marked with this white rod. Now, in this configuration, those 2 axes are skew lines in space. They do not intersect and do not have any special geometrical relationships. However, we could have a special case where they do intersect. Alternatively, they might be skew and at 90 degrees. A further possibility is that they are actually intersecting at 90 degrees. And finally, we might have them parallel. This last case gives rise to a very special type of system. Here we have a model of the parallel case. Again, it has the same kinematic structure as the Puma, with 7 vertices and 6 edges, but all the revolute axes are parallel. How many degrees of freedom do you think this one has? 6? Well, let's see. If I move the gripper here on the end, it can move in the X direction, the Y direction, but it can't move in the Z direction, apart from the slight slack in this model. How can it orientate? Well, it can rotate in your angle, but it cannot pitch up and down or roll. It is restrained. So we have in fact lost 3 degrees of freedom with this special geometry. And now every link will only move in parallel planes. What relevance does this kinematic structure and special geometry have to a real system?
It's one thing to get a welding gun into a particular position and orientation, but usually it has to negotiate obstructions as well. Now, how far a particular arm can work round obstructions and reach inside things is what we call its flexibility. And it's this aspect of manipulation we want to look at now. The flexibility of a system is a function of its geometry, and we can get a measure of it by considering how many different configurations there are for the system for a given position of the end link. For example, I can hold a pen like this with my right elbow down, or like this in the same position, but with the right elbow up. 2 completely different configurations. Now, we find, in fact, that the more special geometry there is, that is, parallel axes, or perpendicular axes, or intersecting axes, the more special geometry, the less flexible the system is. Let's just go back to Joe's model for a moment. This is the one, you remember, that had all 6 degrees of freedom. And for a given position of this end link there, say, there's one configuration, and by moving it a little, I can easily find an alternative configuration for the same position of the end link. And in fact, there are several more. This model has very general geometry. All the axes are skew to each other. And that's what makes it so very flexible. So, if we want to design a manipulator for flexibility, it looks as if skew geometry is what we should be going for.
But the Puma certainly doesn't have all its axes skew. And as we've seen, it's been designed such that some of its axes intersect at 90 degrees, whereas others are parallel. Why, therefore, has such a specialized geometry been chosen? Well, if we look at it performing such an apparently simple task as moving in a straight line, you'll notice that every joint has to move in a synchronized way. And this requires solving many complicated equations in real time, involving thousands of calculations per second. But even with such a special geometry as Puma, how flexible is the system? To find out how flexible it really is, we recorded this sequence earlier on.
We fixed these two pointers to make sure we could check on the exact position and orientation of the gripper throughout the demonstration and see that they didn't move. Well, this is one configuration of the arm, and we'll keep a note of its outline. And let's try another configuration now. And you notice that the gripper's gone back to the same position, but the arm's got a different configuration now. Let's take a note of this new configuration. And then we'll try another. And you can see the gripper's gone back to the same position, but the arm, although it looks similar, is in a completely different configuration, as you can see, because you can now read Puma's name. And here's yet another configuration, but with the gripper again having gone back to exactly the same place. So that's 4 different basic configurations of the Puma for a given gripper position and orientation. And in fact, we can get another 4 because for each of those, there's a wrist flip Puma can do, and that would give us 8 configurations in all. Well, now, it's recently been proved that in theory, for a system with Puma's kinematic structure, but with completely general geometry, you can get 32 different configurations for a given end-link position and orientation. But nobody's ever built a practical system like that. It would just be too complex a job to control. And in fact, Puma represents one of the best designs available at the moment, especially when it does tricks like this. Cheers.
Cheers.